All right. Welcome. This is ARC205. My name is Paul Underwood. I'm a solutions architect dedicated to startups. I'm based in Austin, Texas. Any Texans in here tonight?
Yeah.
Yeehaw. All right, y'all. Over here we got John Kelty. He is the chief bioinformaticist for Third Rock Ventures, and he'll be talking here in a minute. For those of you who, just FYI, this session is also cross-listed with life sciences. So for those of you who are here for that, John will be talking about that here at the sort of second half of the presentation. So what I'm hoping you walk out of here today is sort of understanding or developing sort of better understanding of how startups are building on AWS. And I think that's important. Part of the reason why I want to communicate that message is because whether you work for an enterprise or a startup or a medium-sized company, there are lessons to learn about the way that startups build things and how you can apply those in your own company. So sort of first off, I want to set some expectations that I have of you as the audience. I hope all of you are aware of kind of the 100 level AWS constructs. I'm presuming you guys know what Lambda is. I'm not going to spend the time explaining what Lambda is, so just keep that in mind. What we're going to do here is we're going to cover 3 different architecture patterns: in-tier, containerized, and serverless. And we're going to talk about the implications that those choices have on the cost, performance, and your team structure. And then we'll wrap it up with John from TRV to talk about his journey and what it's been like launching 44 startups over the last 10 years. I think that they're, again, having a perspective of the way that VCs look and launch companies is that at that rate, again, I think is very relevant whether you're a startup, thinking about how VCs look at you, or if you're at a large company, thinking about how you can support the business units that you work with and how to potentially sort of create mechanisms to sort of support the people that you focus on. So what are startups really thinking about? This is sort of my experience over the last 3.5 years working with accelerator-backed startups, VC-backed startups, that they all tend to have these 4 kind of core elements, right? They're all expecting to become the next Instagram. They all want to be the next Instagram or what have you. There's a focus on features. Everybody's really interested in building the sort of core value prop of their company. They don't want to spend their time focusing on glue or focusing on the stuff that isn't really true value add. And then almost universally, these startups have very lean IT departments, right? Maybe one guy, maybe a couple of guys, very lean. And they're also very conscious about cost. A lot of these companies have raised a little bit of money and they're looking to they're looking to stretch that dollar as far as possible. But we're all actually thinking about that, right? Those are the same. We're all doesn't matter what company you work for, we'd always love to have more people in our IT department. We're always concerned about cost. We always kind of anticipate or think about how to scale the things we're developing and working on. But we all come to reInvent because we have other things on our mind. We're looking at how to make sure our architectures are reliable, how they are performant, how cost efficient are they, what's security look like, and how are you operating your architecture on a regular basis in a way that's repeatable and efficient. And now these also map directly to our well-architected pillars. For those of you who are familiar with well-architected program or done a well-architected review, I'm sure you guys have answered a lot of questions on this front. And I would argue that putting all of these things together is what is a sort of indication of a successful startup. And hopefully this talk will show you guys the way that I see startups aligning these things on a regular basis every day. So how have people been building these things, building architectures historically using these kinds of frameworks? Flask, Express, Spring, ASP.NET, Ruby. And this is the conventional in-tier architecture. You're probably all very, very familiar with this. The idea is that you have some kind of load balancer at the front where all the inbound ingest traffic is coming. You have your application servers generally spread across multiple data centers so that if one fails, things still work. And then you have your database tier where you're replicating across to that other data center in the event that something goes wrong there. This is a conventional in-tier architecture that I'm sure most of you are familiar with. So how do startups do this on AWS? Well, we have a service called Elastic Beanstalk here, and you can see these set of sort of commands here. The first thing that we're doing is we're kind of cloning our repository out of Git. Then we're running that eb init command, which is actually going to launch an Elastic Beanstalk environment, or sort of initialize your local directory to start working as a Beanstalk directory. The eb create prod is the command that will actually begin launching the underlying EC2 instance and load balancer. In this case, we're running pg restore to move a pg dump file into the database that our Elastic Beanstalk environment has created for us. We're setting some kind of shared key or setting environment variables that we may need to. And at that point, the application is up and running. Now, let's say I need to start making changes to that, and I can run eb create test, which will create a whole separate environment, a brand new load balancer, brand new application servers that are completely separate. You can then sort of make your changes, commit your profound changes, and then run eb deploy, and that will deploy all of that code onto those servers for you. So you can see in this process, there's nothing I had to do here to launch an actual server. Elastic Beanstalk handled that all for me. And when I run eb deploy, because I've initialized my local working directory as a Beanstalk directory, it will automatically deploy that code for me. I don't have to deal with that. And let's say I'm happy with what I see in test and I want to promote that to production. I can run eb switch prod, and that will switch me over my local working directory to point to the production environment, and then eb deploy will actually deploy that into that production environment, those changes that I just made. And so what all those commands give us is this. It gives us an Elastic load balancer. It gives us 2 application servers. It gives us a RDS instance if we want to, and it also automatically separates those and runs those in 2 different availability zones. And you can see when I ran that eb create test, it actually created a whole similar stack in a separate environment from my production. But it also gives you some significant benefits on top of that, right? It allows you to, it's very easy to apply identity access management. It handles a lot of the VPC networking complexity. AWS CloudWatch is automatically set up to sort of log events that are happening in your stack. And it also allows you, Beanstalk will allow you to define other properties like S3 buckets and things like that through the eb configuration extensions that will allow you to set up a Redis cluster if you needed to do caching. And again, that can all be done through that Elastic Beanstalk command line interface. You don't have to go through the console to do all of this. I like to call Elastic Beanstalk sort of the cheat code to making in-tier architecture easier on AWS. It really builds you into the best practices from the start. So if you're thinking about in-tier architecture and you want to go down that path, use the Elastic Beanstalk command line interface. If you start getting more sophisticated with your continuous integration or continuous deployment tool chains, you can use the Elastic Beanstalk CLI inside of those scripts that you write, and again, it just helps you automate a lot of that plumbing that you do on your own. So let's talk about cost for a second. The Elastic Load Balancer itself is roughly going to cost you $18.30 a month. Your development environment, you might want to run that on T2 micros, so roughly around 10. And your database server is going to be, roughly $23.95. So, roughly $50 a month for your development environment. Your production grade stack, I really recommend M4 large is sort of that minimum production grade instance size. And so you can see the cost there roughly around $320. And you can see we've got 2 databases in the database tier because we need that high-value replication. Whereas our development-grade stack, we only need 1 instance because it's just development and we're not really concerned about reliability. So that's in-tier architectures, so we'll kind of place those here. We're going to move on now to containerized architectures next. And this is, I think, sometimes lost on people. They think about Docker and they lose sight of the fact that really, in theory, your in-tier VM-based architecture looks very, very similar to a container-based in-tier architecture. You're still going to have a load balancer, but you'll be running inside that a Docker container. Maybe you're running your application servers in sort of that middle tier, and then maybe you're running your database inside your Docker containers as well. And all of those containers are sort of running on underlying container instances at the end of the day. And so that's in theory, but in practice, we strongly recommend that you take advantage of the AWS ecosystem. Instead of running your database and your persistence tier in a Docker container, take advantage of the reliability features like multi-AZ and read replicas and use something like RDS. Your application load balancer, also there's some baked-in features that make it very easy to do things like SSL termination and Route 53 aliasing for avoiding static IP addresses and things like that. So take advantage of the platform when you're thinking about running containers on AWS. So very similar to what we did for the Elastic Beanstalk command line interface, there's actually an ECS command line interface as well. So the way ECS works is you'll run that AWS ECS get login command that will actually sort of log you into the Docker repository. Running Docker build will allow you to sort of build your Docker file and tag it. The next thing that you can see here is the ECS CLI is actually sort of running the sort of necessary commands to begin launching instances. The ECS CLI also supports compose. So if you have a Docker compose file, you can point the ECS CLI to that, and it will do all the necessary stuff to set up that task definition, although it won't set you up with the automatic application load balancer or auto scaling group. There's actually a ECS create service, which is instead of the ECS CLI, the ECS that just comes native inside the AWS command line interface tools, will allow you to define more sophisticated services using a service definition file, and that's effectively what that command looks like down there on the bottom. So point in here is that there are command line tools available to you both for Beanstalk and ECS, and you should really try to take advantage of that. So similarly to the Elastic Beanstalk, what is ECS giving us, right? So on the left side here, we have the assets. We have our Docker files. We have our Docker images that have been checked into the repository. And we have our services and tasks defined. We give those basically to the ECS scheduler. And the scheduler will take all the responsibility for running those instances running those containers on the underlying container instances. And the service definitions will allow us to include things like the application load balancer. Now, it's important to note here that the database tier is actually managed by RDS. There isn't a similar feature for the ECS CLI like there is in Beanstalk to launch the RDS environment. So that's sort of up to you to manage that database tier on your own. A couple of other things to consider, though, when you're working with containers. You need to start thinking about things like service discovery. Really, we recommend that you use Route 53, potentially for the sort of native AWS service discovery feature. Console is also very popular amongst the startups that I work with. Container instance scaling is also something you need to consider. So you need to both scale elastically your container instances, the underlying EC2 boxes that are running, those need to be in auto-scaling groups. But you also need to have container instance scaling so that it actually adds more containers as load increases. Over the last 2 years since ECS has been out, there's been a lot of the sort of features that we're missing are now we've developed, they're now available. So our container instance scaling is now available within ECS. And you also need to think about logging when you're in your containers. The same way that you log your application files today or your application logs today, you'll want to consider doing that as well in your application tier. ECS itself doesn't do that for you. That's something you still need to do on your own. So what does this cost? You'll look at, so these are both 2 production grade stacks, and you'll see that the price of these is basically identical to what it was on the VM-based tier. The difference here, though, is that we're able to run our ECS stacks, our ECS clusters, at much higher utilization. I may not want to run my traditional VM-based architecture at above 40% utilization. In the event that one box fails, all of a sudden I'm going to be running at 80% of capacity on the box that's still living. And that's a concern. In the event that traffic picks up after that point, you may find yourself sort of having resource contention issues. Whereas with ECS, because of Docker's shared model, you can start thinking about packing those things in a little bit higher. So while it may cost you the same amount, you're able to run at a much higher utilization rate than you would sort of be able to do comfortably in your in-tier VM-based architecture. All right, so now I'm going to start moving into maybe a little more philosophy here. This is the sort of what I call the stack challenge. And this is sort of my opinion. Please come find me afterwards if you disagree with this. But VM and container-based architectures are rooted in emulating classic physical servers. And because of that, you inherit the stack challenge with either architecture. You have to start thinking about server-level configurations. What patches do I have installed? What are my users and groups who are allowed to log into this box? The files, bootstrapping those individual boxes. These are all complicated things that you have to think about because we're sort of emulating what we had to do historically on these classic physical boxes. And then when you're using ECS, there's another couple layers of additional stack challenge that you have to deal with when you're thinking about, well, I'm running my containers, but I still have physical, I still have VMs that are running these containers, and I still need to think about all of the things above here on my ECS instance. So even if you're choosing Docker to avoid some of the stack challenge or to simplify the stack challenge, you're still, at the end of the day, inheriting a lot of those complexities. So tooling can get you so far, right? Chef, Ansible, Elastic Beanstalk, all these tools make it easier for you to manage the stack challenge. But as things grow and complexity increases, you need DevOps staff. And I would argue that developers are different beings than DevOps engineers. Your developers are going to be focused on those features. Your DevOps engineers are making sure that you're achieving that operational excellence. And so what ends up happening is you start getting this bifurcation of responsibilities. Your developers are working on feature 2 after they've shipped feature 1 to test, and all the while your ops team is actually dealing with deploying feature 0. And this starts to look like a conventional software SDLC that nobody really likes or enjoys. And what's the rushing sound, so to speak? So AWS thinks about this, and we see our customers sort of suffering and dealing with these problems, and so we start thinking big and start thinking about ways that we can simplify these things, right? And we pose sort of a couple of questions and answers here. So if we all agree that containers and traditional VM-based architectures are rooted in emulating classical servers, why should anybody care about servers? Why shouldn't we all just treat them like cattle instead of pets? The feature development is way more valuable. Everybody's focused on the feature. Nobody wants to write glue code. And why can't things just scale automatically? Why do I need to sweat what my utilization is for my particular stack? These are just things, these are challenges that everybody's had to suffer through. So I want to give a little historical perspective on the way things have evolved over time. The ENIAC came out in 1946. It's actually at the Smithsonian in DC, and when I saw it a few years ago, they had R2-D2 and C3PO right next to the ENIAC. It was a really cool shot. But in 1979, CH root process isolation came out, sort of made it possible to start running sort of slicing off your operating system into smaller and smaller pieces, and this was done at the time to simplify sharing resources amongst, sort of limited resources amongst a group of people. Later on down the road, that actually paved the way for containerization as we know it. And that, that also led the way to sort of VM-based architectures, where in 2006, we came out with EC2. And the blue dots here, in my opinion, are really where sort of modern startup adoption really started to pick up for these different sort of pieces of technology. So 2009, elastic load balancers came out. 2010, RDS came out, making databases a lot easier. But you'll see all of these things are still rooted in that server-centric architecture. So what's next? And I think you all probably know what's coming, and that is serverless architecture. So what does a serverless web architecture look like? So on the left side here, you may have you have your end clients, your screens of various types, going to example.com. You may choose to use something like an Angular single-page web application or what have you. Store that inside your S3 bucket by enabling website hosting on your S3 bucket and put CloudFront in front of that. And that will host basically your entire front end, as well as your images or your HTML, your JavaScript, things like that. And that on its own can stand and scale automatically. There's nothing that you need to think about in terms of scalability or, or availability of your boxes, because Amazon CloudFront and S3 handle those things for you. But I need an API to back up that front-end application. And so let's say all those API requests go to api.example.com, in which case I can use Amazon API Gateway, which is another serverless service that allows you to define your APIs in a very straightforward fashion, either visually through the editor or through the web console, or through I'm blanking on the name of the supporting document, but then you may back up API Gateway with AWS Lambda, and Lambda being your sort of main compute element that handles the dynamic requests. I need some kind of storage persistence tier, and so in this case I can use Amazon DynamoDB for sort of my persistence over time. So sort of a NoSQL database, and that's where AWS Lambda sort of writes any data that I need to store. So how are startups building this architecture on AWS today? Well, there's a plethora of options out there today, right? So we have our own serverless application model. Our serverless application models allow you to define basically everything you just saw on that left side in a CloudFormation template. It's actually an extension of CloudFormation's templating language, but it'll allow you to define API gateways. It'll allow you to define Lambda functions as well as DynamoDB tables, and can really simplify that. Another very popular approach is to use tools like serverless or standard lib is another one that's great. Actually, Keith Horwood from standard lib presented this talk with me last year, so big shout out to him. I'm not sure if you're here, Keith. Thank you, though. But these are all sort of options that are sort of evolving to sort of make developers' development experience and development workflow much, much easier. So what does this cost per month? And this is where I think it gets really, really exciting. I can't tell you that it's going to be $320 a month for a server, because there's no server here. So what I've done here is I've sort of created a example customer usage pattern. So imagine one of your users goes to your website and hits 10 pages over the course of the day. Each page is roughly 200 kilobytes in size. There's about 5 API requests per page. The average size of the API requests is relatively small, and the sort of number of operations in and out of that DynamoDB table is also relatively small. One read, one write, per API request. And we need to store roughly 500 kilobytes of data for that particular user over the course of the month. Well, here's where it gets exciting. We can calculate what it is per request. right? I can tell you what that individual customer is going to cost me at the end of the month. It's a completely different model than thinking about jamming all of my customers into one box and then dividing that by the amount it costs me per day. You can really do the math and think about what it's going to cost you per user per month, and that can completely change your economics. And so I really encourage you guys to change the way you think about pricing when you're dealing with serverless, and try to think of it more in this fashion, because it's possible to do this today, whereas years ago this was a message, sort of exercise in futility. So moving more into sort of the team structure element that we talked about early on, and sort of pushing you guys into what's more known today as sort of microservices. And this is what a microservice might look like for a startup on day one. You have this sort of same architecture that we already went over, and maybe it's just one developer. And that one developer is responsible for all of these pieces, the front end, the back end, the API gateway. But what's also important is that startup is probably, and it should be responsible for all phases of the SDLC himself. He writes the code, he or she writes the code, they test it, they operate it, they maintain it. It's their responsibility. And I think that's a core element in microservices architecture. The SDLC is no longer broken off into multiple teams. The team that writes the microservice is responsible for the entirety of the SDLC for that particular service. Now, this developer is going to get wiped out after a while. That's a lot of work for an individual to do. And so what you have here, as complexity starts scaling up, you may need to have another microservice that handles just the API portion, and you have that original developer just responsible for that front end. And when is the right time to perform that mitosis of responsibility? Well, at Amazon, we have something called 2 pizzas. If you can't feed the team that's responsible for that microservice with 2 pizzas, you have to bifurcate that. That's the time, that's the signal for you to start thinking about breaking off a piece of that into its own microservice. And so as things go on, as complexity continues to scale, we may have several teams at this point, several different microservices, several different individuals. And this is really what I want to really reinforce around microservices thinking, is that if you're the manager of a microservices organization, you really need to let your teams pick the right tools for the job. If they're responsible for all phases of the SDLC, when things break, they're the ones that fix it. So empower them to make the right choices. So in this case, maybe all of the service teams decide, hey, we need to use Lambda, DynamoDB, API Gateway, S3, just like we talked about purely serverless. But in reality, it might be that service team 1 prefers to use ECS or use Docker because they find that there's a lot of value add or a lot of value available within for their particular service they're responsible for to use ECS. Where a service 2 might be a little more akin and familiar with VM-based architectures, and maybe they've done the math and figured out that the request rates that they need to support are high enough that maybe Lambda doesn't make sense. Lambda might be too expensive at the 10,000 requests per second, and they might want to use conventional in-tier-based architecture. And then on the far left here is sort of the chess piece represents what I'll call your sort of enterprise architect. Your enterprise architect should be responsible for handling things like Route 53 and API Gateway. Your lead architect or your head architect can define your contractual RESTful interfaces between all of these microservices and have great, strong visibility into the entire sort of responsibility of the way that these services should be talking together. They can define the interface and then let the teams do the implementation. And that's a really strong position to be in, because that key architect doesn't have to be responsible for implementation, but they can really lay out the way that everything should be working together. And then as complexity grows, you might have your big data guy comes in. And your big data, let him choose what services he should be using. Let him use Athena, which is one of my favorite personal services right now. Maybe he uses EMR. Maybe he uses Redshift. They're a different breed of animal, so let them choose the services that they want. And your mobile developers may have their own sort of individual pieces of technology, but let them own the entire phase of their own piece of the SDLC whenever possible, because that's a core element that is often forgotten about in microservices architecture. So with that in mind, I'm going to pass it over here to John Kelty from TRV. I mentioned that that Third Rock Ventures has launched 44 startups over the last 10 years or so. And John's going to bring brings a lot of fascinating perspective on how VCs and Third Rock approach the startup ecosystem.
Awesome. Thanks, Paul.
Yeah.
So now for something completely different. Like, how do we take everything that Paul talked about and how do we actually use that in reality in startup companies? You're going to hear a little bit about biotech startups, which are a little bit different than tech startups. And so bear with me for a second while I just sort of give you a brief history, just so you have some context. So Third Rock Ventures was founded in 2007. Ironically, it was founded based on a discussion at a blackjack table here in Vegas. It was the three founding partners, got together and were lamenting the fact that large pharma, they felt, had really lost their innovation. And as a result, we wind up with patients that should be getting drugs that aren't getting them because we're not driving these things in the right way. So, with that in mind, they went back and tried to raise some money to maybe start a company, ended up raising almost $500 million and decided to put that at work at a variety of companies. With the mandate of let's focus on the patients first, let's build companies based on innovative science. And the process is pretty straightforward, right? We take really disruptive science, whether that's cutting-edge genomics or state-of-the-art computational chemistry. You marry them up with the best people, and then you mix that all together in a process that allows these components to work together in a robust way. And the best people don't just mean the tech people, right? It's also the best scientists. It's it's the best BD people, right? All these sorts of things come together to have a company that not only is there on a given day, but can be here 15, 20 years from now, which is the mandate that we have at Third Rock. So what does our process look like? It's pretty straightforward. So anyone that's been in a pharma company, you always have this funnel of stuff that comes in and stuff that comes out. Third Rock operates somewhat similarly. The ideas for the companies can come from anywhere. Sometimes there's great ideas from academia. Sometimes there's great ideas that are just gestated internally. And we go through a fairly robust process, high level of scrutiny, to get that down to what we hope is a steady state of about 3 startups a year. We've actually been at a slightly faster pace than that. And so what does that look like? What does the landscape look like right now? So we're right now on our 4th fund. And again, each fund has been incrementally larger than the last. And there's a couple things to note here. So it's cool, right? We've been successful enough that we're able to raise these additional funds. We've had some very successful companies. That's all well and good. For me, it's interesting to look at the patterns here. With Fund 1, we had an interesting mix of companies that range from product companies, but also some diagnostic plays and things like that. That has changed. And so now when you get into Fund 3 and 4, it's entirely product companies. And we'll get into why that's important. Maybe equally or more important to people like me is that with Fund 1 and Fund 2, we would go in and we would invest in a company with a consortium of 3 or 4 other venture firms, which is awesome, right? Because you can go in there with a smaller number. You invest 10 instead of $50 million, which is fantastic. The sad side is then when I want to do something like we're going to push to the public cloud, I'm arguing with 3 or 4 other venture firms that say, oh, no freaking way, that stuff's not safe. And so the progression has been, with Fund 3 and 4, has been we're going to do this ourselves. So Third Rock goes in with $50, $60 million, which may seem a lot to a tech startup. That's not a lot for a biotech. That'll get you, 2 or 3 years if you're doing a brick and mortar biotech company. But what we get is a group of people from Third Rock that are on the management team that are making decisions, and it enables people like myself to go in and say, well, this is just the way we're doing it. And then there's, okay, we're just going to do it. So that's been pretty empowering. And so, what has been our thinking as we've gone into that? So number 1, big push to the cloud. That really started happening for us about 4 years ago. I wish it had happened earlier. These startups, before that, what would happen is we would spend $300,000 to $500,000, build out a server room, which either was a little too much or way too little, and then you had to blow this out. So, biotech startups, it's perfectly logical place to be applying the elasticity and scalability of the cloud environments. For these startup companies, we'll typically go out after the Series A, and we'll have a team of 13, 15 people. Maybe you grow to 30 over year one, and then there have been some very successful companies that 7 or 8 years in now are 500 people. But to start with, we don't have any technical people, right? So we have oftentimes an army of one that is responsible both for the IT piece. Lots of times these folks, we try really hard to get people that are well-versed in software engineering and or really understand the life sciences, but there's just too much on their plate. So we really gravitate towards finding the right commercial off-the-shelf systems. And that's not to say you don't need software development, because we do. But we leverage that primarily in ways of integrating data from these commercial off-the-shelf systems and marrying that data together so that we can answer questions that you couldn't with these independent systems. And the other thing that's been really important that we've been able to do is, because now we've got a general framework and playbook, we've been able to put together a team of high-powered consultants and full-time Third Rock employees to really drive this going forward. So we're really clever, and we call that the Trv Platform Team. And the mandate it's pretty straightforward. So while these individual companies, as we're starting them up, don't necessarily have the technical expertise in-house, we'll provide it for them. Let's make sure we get the foundation right. Because what was happening, circa Fund 2 is, 2 years in, somebody like me would have to go in and do a rip and replace on everything that was put in place in terms of infrastructure. So, biotechs, like, a lot of us in this room in various industries, deal with data that is eclectic in nature. There's more and more of it. Lots of biotechs leverage data that's not only generated in-house, but, grabbing public data from a variety of sources, especially with this advent of personalized medicine. And what does that mean? Well, when we put together solutions, at least historically, you approach this with a scientist mentality, which is very reductionist. It's kind of sad, right? And we have this big data thing. When you're, in a biotech or pharma company, the scientist still says, I have a question, I have a hypothesis, I'm going to do an experiment, I'm going to answer that experiment, and I'm good to go. In an early stage biotech, there's so much pressure on these guys to just deliver, get something into the clinic as fast as you can, that lots of times we ignore the need for putting the data together in a way that we can mine that in the future. So there's a general lack of focus on long-term data integration. So this got us to thinking, like, how can we do a better job with this, right? And while we're calling this biotech blueprint, I think it's actually applicable to any startup, right? And our initial focus in terms of coming up with the framework was to focus first on security, identity management, VPC configuration. And what you see here is relatively straightforward, but for an early stage biotech company with no one there, and the worry of senior management that, this cloud stuff is, it's not secure enough, we're able to lock that down in an effective way where we've got a simple 2 VPC setup with both a development and a production instance. Lots of times we'll add in another VPC fairly quickly, and all that stuff's scripted. So, while we talk a lot about cost, right, and I know Paul emphasized that, and that's awesome, we want to do things as cheaply as possible. My biggest worry actually is time, right? So if we're starting a biotech company, we would typically spend months to sort of build out the infrastructure before you could really hit the ground running. So what we can do now, what used to take to set up, the servers and the systems would take months, now we do that in minutes. And that's been huge. Lots of times, for those of us on the East Coast and the Boston area, space is kind of at a premium. And so we are lots of times starting companies, and we don't have space yet. So now what we can do is start up the infrastructure. We're starting to pull in data from vendors, right? We're setting up all of these commercial off-the-shelf systems up in the cloud. And it is, to a large degree, plug and play. The other thing that we've done that has been very beneficial is just to build out what we're calling this Trv Catalog. And that's a mix of templates for things like the VPC. It includes, Lambda scripts. It includes a whole bunch of different components. And what's become interesting is this community that's built up where we certainly have a lot of that is contributed by TRV with the help of the folks at Amazon. Vendors now contribute. And maybe most importantly, a lot of the folks at the various TRV companies who now are a little bit more mature are using Amazon, and they're 3 or 4 years in are going, ooh, that didn't work as well as we thought, they feed that back to the mothership, right? And now the next company that goes out, we can make sure that we tweak this. So already we've gone through probably, 3 or 4 turns of the crank, and each time we get a little bit better. And then what happens ultimately is, we can get the lowest common denominator nailed down, right? VPC, general catalog, and then each company sort of goes off and does their own thing. So a computational chemistry company isn't going to want the same things as a hardcore genomics company, isn't going to want the same thing as a traditional screening company, but the foundation is all there, and it's all the same. So what is also interesting is we can sort of predict what's going to come next. When we look at the companies, there's a very common pattern where as you're starting to spend your Series A money, we're very much focused, like I said, on the fundamentals of the infrastructure. Let's make the security nailed down. Let's deal with storage, right, and make sure that that's working well. More and more in our early stage companies, high-performance computing becomes a dominant need very early. And then we're layering on top of these commercial off-the-shelf systems that should plug and play, right? And these range in lots of cases for our chemistry companies would be, things like chemical registration and things like that. We have systems to support biology, and then, more broadly, things to do lab ops activities. And when we're choosing these systems, that's another one where you just want to make sure, when I'm choosing these, can I pull the data out in ways that I want, right? Is this built on a reasonable enough architecture? And sadly, for those of us in life sciences, most of these systems are pretty poor, right? And so as we're building these, you want to do this in a modular way so we can swap out later. So time ticks by. It kind of varies from company to company, but you enter this sort of hardcore research phase where we're adding in more functions to the company. So this, I have some examples up here where, may have started with chemistry and biology, right? Some lab ops. Well, at some point now, I'm adding in pharmacology, right? I'm testing our drugs in animals and generating data from that. I have a pharm dev group. I have a translational department. So these folks are the ones that are thinking about, how do you take what we're learning preclinically and apply that to how we do our clinical trials. And so we build out the infrastructure to support that. Again, enhance the HPC, really focus on data aggregation and mining, and then build out core services that can be used more broadly. Eventually, and it depends a lot on the company. Some of our companies, it takes a year to get in the clinic. Some of the companies, it's 5+. But there you're dealing with a whole nother set of compliance, right? And I sort of alluded to when you're in this research phase of potential needs for HIPAA compliance. Again, that's another thing that's very easy to lock down for us in Amazon, where, to be honest, when we're asked to do that with the on-prem, with the number of resources we have, it's almost impossible, right? So this is suddenly empowering there. In the same way, once you're in the clinic, you're beholden to 21 CFR 11 and general GXP regulations. Depending on how you configure these systems, we can do all that, right, in Amazon. And we get to that point, you're building out systems to support new functions, right? So that's thinking about groups like clinical, regulatory. So how do we submit things to the FDA? How do we take, data sets that were generated in support of an IND? How do you submit those off to the FDA to get your IND approval? And at the end of the day, we can take a step back and say, well, I can kind of predict now what are the core services that I'm going to need. What are the next things that these individual companies are need? So, that's what TRV is working on now, right? Both the TRV mothership and then, like I said, the companies now that have evolved to the point where they are in the clinic, they can feed that back, right? And we put that into our broader catalog. So I thought I'd give you a couple of vignettes, right? So, what does all this mean and how does this work, right? So Tango Therapeutics is a relatively new third rock company, small, located in Cambridge, and their main focus is developing cancer therapies. And what's cool about this one is they are taking cutting-edge genomics to identify novel targets, right? And at the same time, be able to pick patient populations. So you're going to marry up the right drug with the right patient. And the very basis of how these folks are doing that, you almost find these patients as an offshoot. The data that is being generated by Tango comes both from these internal efforts for screening, but it also comes from external data sets. And so, what we're able to do, because we sort of had the underpinning of Amazon laid out, is at first, in a very serial way, we had a bioinformatics guy turning the crank, analyzing public data, sequence data, that was coming from almost 1,000 cell lines. and was able to turn the crank one at a time. This was taking about a half a day, right, and was trending to be crazy expensive. And so you now take the Amazon team, you take the folks from Third Rock, and you apply this to this, and now we have a system that has leveraging AWS Lambda, you're leveraging batch, and we're able to now have a robust process that is able to take something that originally took, was projected to take over a year to actually crunch through all of these cell lines, and now take that down to 14 days. So you mentioned the cost here. Again, that's not my biggest concern. My biggest concern is can we crank through all of that data and mine that in a way that is going to actually inform where we're going with our drugs. You can imagine, you've got that initial funding, maybe you get 2.5, 3 years. If I'm spending, almost a year and a half, crunching through data, that's a problem, right? So being able to scale that instantly is huge. And one more vignette, right, from a very different company, but equally exciting. So this is a company called Relay Therapeutics. And Relay is developing small molecule therapies that are based on really understanding protein structure, both the static structure and then how these proteins move. And so we can find ways of finding binding sites in these proteins that are non-traditional. So I won't talk to me afterwards if you want to have a little biochemistry discussion. But what this does is it opens the door to getting at important targets for drug therapy that you wouldn't be able to get at before. But in order to do that, you really need to understand the protein structures. And so, what we have here is 3 distinct ways that the computational team does that. So one is taking X-ray crystal structures, right, which is in and of itself is pretty cool. You look at genomics is scaled. Even the ability to do things like crystal structures is scaled, where 10 or 20 years ago you were lucky to get a crystal structure a year. Now you can do this on the benchtop. Now there's huge computational burden that comes with that. So how do we turn the crank on that? And then how do we take what are these static and start to predict how the different conformations of their protein are? So the team at Relay, because they have a kick-ass computational chemistry team, but also have the right framework in place, we're able to now do something that an early stage startup 10 years ago wouldn't be able to do, which is taking 100 of these data sets, crank through 50,000 CPU hours, and get some real answers. Similarly, we can do predictions around free energy perturbation, right? So when you are taking molecules and they're binding with protein, what happens there? And then one of the coolest things lately has been the team over there has gotten access to the P3 instances, these GPUs, and are able to take static images of proteins, almost 500,000 of those, and stitch those together, run machine learning algorithms such that they can now come up with high-resolution 3D images of this, which, again, back to how do I marry up the right small molecule with the right pocket in a protein to make a real difference. So all of this was certainly based on the brain power within these individual companies, but were also a result of having the right framework in place in the first place. And 4 years ago, we were just unable to do that. And this is just the people that actually do all that. So not only do you have the platform team, but as I mentioned, I just want to emphasize one more time, so many of the best ideas actually come from our portfolio companies. I listed a few contributed to components of this deck, but all 44 in their own way are contributing back, and it's a pretty powerful combination. And I will cede the floor to you.
Thank you, John.
Yep.
All right, I just want to leave you guys with a final thought. When you are approaching sort of your next project or your next stakeholder in the company, think about what we talked about today. Think about how to marry all these options together. Think about sort of your microservices architecture. Like John mentioned, there are services that like AWS Batch and the Biotech Blueprint that can drastically facilitate setting up whole new environments that might have taken years in the past. And the sort of final piece that I'll mention is that if, as you're working on small microservices, be it free energy perturbation or genomics processing or just handling a basic sign-up page for a little microsite, if you truly think about things in a microservice way and you take the effort to define what your microservice is and what its boundaries are and where it should stop, it will infer what the underlying architecture should actually be. So, spend that time thinking early on about, defining your microservices and where those boundaries are, and what technology you should use and what architecture you should use to build that will become self-evident. So with that, I will take any questions, if anybody has one, for me or for John. Anybody? We will, yes, sir.
So does there become a tipping point where you go back to EC2 or containers because Lambda gets too expensive?
Yeah, I think if you start looking at the way that Lambda prices the request rates, or sort of the number of requests, and you start looking at those in terms of when you're starting to measure things in like, high thousands or tens of thousands of requests per second, you'll start to see that sort of tipping point starts to flip. So yeah, absolutely. We'll also stick around here for a minute, and then we'll also be outside for a minute if anybody has any questions that they don't want to ask over a mic. All right, thank you, everybody.